The era of pure internal combustion dominance for the Widowmaker has officially ended, but the replacement engineering suggests a capability far exceeding initial projections. The transition to the 992.2 generation 911 GT2 RS introduces a fundamental paradigm shift in the Weissach powertrain philosophy, moving from purely pneumatic forced induction to an electro-pneumatic hybrid architecture. We begin the analysis with the internal combustion component itself. While the standard Carrera GTS and turbo variants have transitioned to the new 3.6-liter architecture, the GT2 RS application retains a heavily modified derivation of the 3.8-liter flat-six architecture to maximize displacement-based torque prior to boost onset. This block has been re-engineered with a deleted belt drive system, as all ancillary components, including the air conditioning compressor and water pumps, are now electrified, powered directly by the high voltage circuit. This deletion reduces parasitic losses on the crankshaft significantly, though the primary objective was packaging. The removal of the belt assembly was strictly necessary to accommodate the pulse inverter and DC-DC converter within the rear engine envelope. The combustion process itself now operates at a stoichiometric lambda 1 ratio across the entire rev range, a requirement for Euro 7 compliance that traditionally cripples peak power output due to thermal limitations. We have circumvented this limitation through the primary innovation of this chassis, the T-hybrid system. The critical component of the system is the integration of the electric exhaust gas turbocharger. In previous generations, the GT2 RS relied on variable turbine geometry, VTG, to mitigate the inherent lag of large frame turbochargers required for high horsepower. The 2026 architecture abandons conventional VTG in favor of a single, large diameter turbine housing featuring a coaxial electric motor mounted directly on the turbocharger shaft between the compressor and turbine wheels. This electric motor, capable of spinning to 150,000 RPM, eliminates the reliance on exhaust gas enthalpy for initial spool up. Upon throttle application, the motor actively accelerates the compressor wheel, achieving maximum boost pressure in approximately 0.8 seconds. From idle, a response time physically impossible for a purely exhaust-driven system of this volumetric capacity. Furthermore, this E-turbo functions as a generator at high engine speeds. Instead of venting excess exhaust pressure through a mechanical wastegate, which represents wasted energy, the electric motor applies braking force to the shaft to regulate boost, recuperating up to 11 kilojoules of electrical energy, which is immediately cycled back into the high voltage traction network. The energy storage solution underpinning this architecture is a 400-volt high voltage system, distinct from the 800-volt architecture found in the Taycan, chosen here for its superior weight-to-density ratio in a sports car application. The energy is stored in a liquid-cooled lithium-ion battery with a gross capacity of approximately 1.9 kWh. This is not a range-extending hybrid battery. It is a performance density unit utilizing cylindrical cells with chemistry optimized for rapid discharge and recharge cycles, behaving more akin to a supercapacitor than a traditional EV battery. Crucially, this battery is positioned under the front cowl, forward of the driver. This strategic placement shifts the center of gravity forward, effectively counteracting the rear-biased weight distribution inherent to the 911 platform and improving front axle load during initial turn-in. The total system weight penalty is mitigated by the removal of the aforementioned mechanical ancillaries and the 12-volt starter motor, as the hybrid system handles engine ignition. Torque transmission is managed by a reinforced 8-speed PDK dual-clutch gearbox. The gearbox housing has been modified to integrate a permanently excited synchronous electric motor, PSM, within the bell housing. This motor provides a direct torque fill of over 150 Nm, essentially from 0 RPM, bridging the torque curve during the millisecond interruptions of gear changes and masking any remaining combustion hesitation. The combined torque output of the 3.8-liter engine and the electric motor now exceeds 1,000 Nm, necessitating the use of high-strength alloy gears and reinforced clutch packs significantly more robust than those found in the standard Turbo S. The integration of the electric motor into the transmission housing also allows for kinetic energy recuperation during braking, working in tandem with the ceramic composite friction brakes. Thermal management presents the most significant engineering challenge in this vehicle. The rear engine layout already suffers from limited airflow, and the addition of the T-hybrid components introduces significant heat rejection requirements. The high-voltage battery requires a dedicated low-temperature cooling circuit to maintain optimal cell temperatures during sustained track abuse, where discharge rates are nearly continuous. Simultaneously, the e-turbo and the transmission-mounted electric motor generate substantial thermal loads that must be dissipated to prevent derating. We have implemented active air flap control in the front fascia and significantly larger intercooler ducts in the rear fenders, utilizing the pressure differentials created by the new aerodynamic package to force feed the heat exchangers. The system is designed to maintain peak output without thermal throttling for sustained lapping sessions at ambient temperatures up to 30 degrees Celsius. In conclusion, the engineering verdict regarding the power-to-weight ratio is definitive. While the T-hybrid system adds approximately 50 kilograms of mass compared to the previous 991.2 generation, the net power output has increased disproportionately, now surpassing 700 metric horsepower with a torque curve that is effectively flat from 2,000 RPM to redline. The result is not merely an improvement in the static power-to-weight ratio, but a radical expansion of the area under the power curve. The vehicle accelerates with the immediate response of a naturally aspirated engine while delivering the relentless top-end thrust of a forced induction flagship, validating the hybrid integration as a performance-enhancing necessity rather than a regulatory concession.